Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on hydrocarbons. This is topic 14 for the CIE, that's the Cambridge International's course. So if you're studying the CIE exam or the syllabus, then this video is perfect for you. And in fact, there's a full range of videos for year 1 and year 2 chemistry, all on Allery Chemistry YouTube channel. Just hit the subscribe button, that'll be massively appreciated just to show your support. All these slides here, these are actually just PowerPoint slides, and they are available to purchase if you want your own copies of them from my test shop. They're great value for money and great to kind of complement your revision material. If you click on the link in the description box below, you can get a hold of them there. But obviously I'll kind of talk through the main content of this. Okay, so let's make a start. So obviously this is topic, like I say, topic 14, and it's to do with hydrocarbons. So hydrocarbons, probably the best place to start before talking about anything else, is hydrocarbons are basically compounds which are made up of hydrogen and carbon, basically, which is quite a lot of molecules, and obviously it fits within the organic chemistry topic. You'll find as well a lot with this, particularly with the CIE topics, is the topics kind of blend into each other. There's a lot of overlap, you know, they kind of rely on information from previous topics to know this one. So make sure you're familiar with particularly the introduction to organic chemistry, AS organic chemistry, which is the previous topic, which is topic 13. So many topics now. So topic 13, to make sure that you understand the basics of what organic chemistry is, and obviously the topics after this then kind of build up from that video as well, from that topic. So let's start with this first. So this is an introduction to alkanes first. So alkanes are classed as saturated hydrocarbons. So what that means is they have no double bonds, basically. There's no double bonds in them at all. And they have the general formula of CnH2n plus 2. Now alkanes are hydrocarbons. They obviously contain carbon and hydrogen only. They're saturated, as I mentioned before, so there's no double bonds in there. And they're actually bonded, each carbon is bonded 4 times. And obviously it produces your alkanes, as you can see there. So you've got methane, ethane, propane as an example. You also get cycloalkanes as well. Now that's basically, they're still alkanes, but you basically form it into a loop, as you can see there. So there's your kind of your cyclic compound. So this is cyclopentane, and all you do is you put the word cyclo in front of it, and obviously how many carbons are in there? That's 5, so that's pentane. Now they have a slightly different general formula, and that's CnH2n, mainly because 2 of the hydrogens are removed to make it into a loop like this. Okay, and cycloalkanes, like I say, they're still saturated. They don't have any double bonds in there at all, so each carbon is bonded 4 times, so it's still classed as a saturated compound. Alright, so let's look at where we can get these alkanes from and kind of the properties of alkanes. Now alkanes are, well, the vast majority of alkanes are actually found naturally in crude oil. So crude oil is obviously a natural gas for that matter. So obviously this is what we can extract from the ground or from under the sea. And actually we can get the alkanes, we can extract them from the ground and we can separate them out, because oil has a mixture of different hydrocarbons in there. So each hydrocarbon has a different property, so it's important that we can separate that out to get each individual alkane, or what we call fraction. So like I say, it's found in crude oil and there's a mixture of them, and this is an example of a fractionating column. So basically what happens is the crude oil is vaporized. So once it's dug out the ground, it's vaporized in a furnace, and you can see it goes in here and it's heated to about 350 degrees Celsius. So crude oil's got a mixture of different hydrocarbons in there. And then once it's been in there, it then enters the column. So it goes in at the bottom here, as you can see there, and it rises through the trays. So obviously it's vaporized. Some of it will be liquid and some of it won't be. But the longest hydrocarbons don't actually vaporize. They kind of fall out of this as a sludge or as a liquid and kind of sink to the bottom of the column, which is about 400 degrees Celsius. Anything which is a gas will kind of rise upwards, up through the column. Now, the column has a temperature gradient, so you can see it's getting cooler as we get to the top. And as the vapor rises, parts of the mixture condense at different temperatures. Okay, so depending on when the gas condenses back into a liquid and at what temperature it does that, will depend on which tray it will sit at, basically. And the reasons for that is actually your longer chain hydrocarbons, so the ones with say 15 to 19 carbon chains, are have a higher boiling point, and so therefore they will condense first at 370 degrees Celsius. Ones with shorter hydrocarbon chains will actually remain will be a liquid a lot higher up, so it'll condense at this point. Some of them won't condense at all, even at room temperature, and actually will still come out as a gas at the top. Now, obviously what we get, this is quite useful because it means we can then take off the different fractions. These are called fractions that come off here. So off here you've got 20 to 40 carbon chains coming off here, 15 to 19, 11 to 15, 5 to 12, and then 1 to 4, the shortest carbon chains, come off at the top, and your longest ones, 40 plus, kind of come off at the bottom here. So what we're doing is we're taking a mixture of different hydrocarbons, putting them through a fractionating column, separating them out, and we're getting different chain lengths. So it's a bit like a big filtration system. So like I say, the gas will then come out at the top there. And you'll notice we have different products that are produced, I suppose, on the back of it. So you've got natural gas, which sits at the top, petrol, kerosene, diesel oil, and fuel oil. And then you've got anything towards the bottom is normally things like asphalt, so bitumen, for example, which is used to make tarmac. You might get wax, paraffin wax, etc. coming out the bottom. So let's have a look at some of these different uses and what we can actually do with them, because it's quite a big industry, the petrochemical industry. So obviously gas comes off right at the top, is used in LPG, that's liquefied petroleum gas, and stove gas. So if you have a barbecue, if you have like you might have a gas cylinder that powers the barbecue, gas that comes into your home if you do have gas coming into your home. So these are fractions that come right at the top of that column there. Petrol's the next one. That's pretty obvious. That's just used in cars. Kerosene's used in fuel, jet fuel. Has a slightly longer hydrocarbon chain, a little bit more energy in it. Diesel oil is used in trains, normally ships, so it's quite heavy oil. Fuel oil, there you go. Fuel oil is used in ships. So diesel oil is a bit thinner, so fuel oil is quite heavy, so lots of energy in there. Obviously, a ship can't be refueling all the time; it's out to sea quite a lot. And then, obviously, finally, the one that comes off right at the bottom is bitumen, and that's used in roofing and tarmac, etc. So all of these have come from crude oil, and we separate them out to provide different uses. And obviously, that pretty much runs at the moment our day-to-day life. We rely heavily on fossil fuels to do all these things. So you can see it's quite a useful product, I suppose. Sometimes though, some of them products, it's a bit potluck. So you get your crude oil, and it's got loads of different hydrocarbons in there, and you might end up getting, maybe, let's go the extreme end, let's say you get 80% of that fraction of that oil is actually tarmac or bitumen, and the rest of the 20% is kind of the higher up fractions. Now the problem with that is that might be fine if you've got a massive road building project and you need all that kind of tarmac to do that, but in reality that doesn't really happen. And obviously there's still a demand for fuel and petrol and things like that, and natural gas. So there's this technique whereby we can actually break down or cut bigger or longer hydrocarbon chains into smaller, more useful ones to meet consumer demand, and we call this process cracking. So cracking is basically, as it suggests, cracking is to crack or break a molecule apart into shorter, more high demand products. So, like I say, obviously you've got fractional distillation is fine for separating it out, but sometimes we want to try and produce products that serve a demand. So your heavier fractions, like fuel oil and bitumen are in lower demand than your lighter fractions, which is petrol, which is likely to be in higher demand because we drive cars and lorries and trucks, etc. So we can take them heavier fractions and crack them, and basically break the longer hydrocarbon chains into the shorter ones. And here's an example. So you got dodecane, which is a hydrocarbon with 12 carbons in there, and we can break that down into two parts. We can form decane, which is C10H22, so that's a shorter chain, and we form an alkene as well, which we'll look at alkenes later on. So that's C2H4. So there's two types of cracking. You've got thermal and you've got catalytic cracking. So obviously two are slightly different. I'm going to look at each one in turn and look at the difference and why they're actually important. So let's start with thermal cracking first. So as the name suggests, it's heat. It's something to do with heat. So high temperatures are needed for this type of cracking. We need high pressures as well. About 70 atmospheres of pressure. So that's quite a lot of pressure. And the products of thermal cracking are mainly alkenes. Okay, so we don't really produce a lot of alkanes, but we produce an awful lot of alkenes. Now, alkenes are useful because we make plastics from it. We make polymers from that. And obviously propene is used to make polypropene. So, a really useful method. But as you can see, it's probably going to be quite expensive because you need a lot of heat and a lot of pressure. So we have to make sure that if we are using this to make plastics, then obviously, it's worth it. There's obviously a tendency to try and recycle plastics rather than, make new plastics from raw materials, because obviously these are finite resources, but also because of the cost. The cost of making new plastic is quite expensive, as you can see. So the other type of cracking is catalytic cracking. Now, as this suggests, we use catalysts here. So high temperature and a slight pressure is used. So the temperature is 450 degrees Celsius. But a zeolite catalyst is used, and that helps to lower the temperature needed. Now, if you remember back in some of the previous topics where you looked at energetics and looking at using catalysts to reduce the energy required for, it obviously alters the pathway, doesn't it, for a reaction to happen. It means less energy is required to get that going. Then catalytic cracking or catalysts help to do that. Now, normally the products of catalytic cracking are mainly what we call aromatic hydrocarbons, and this is useful in fuels. So aromatic compounds are basically benzene rings. Now, you won't see benzene ring you won't see it very, quite rarely actually in year one, but if you're doing the full A level and you're going to do year two, benzene, you'll learn a lot more about benzene in year two. So using a zeolite catalyst, which is a bit like a solid catalyst with loads of pores in there, that obviously lowers the temperature and the pressure, so that lowers the cost. It's more environmentally friendly and it speeds up the process. However, you're not producing alkenes, which could be used to make plastics. So it depends what you want from it as to which process is probably the best one to use. Okay. So on the back of that, so we've got our alkanes, we've extracted it from from crude oil, and we've cracked it to get the right ones. We need to use it for something, and obviously one of the uses we'd seen before was the combustion of alkanes. Now we're going to look at reactions of complete combustion of alkanes to show what happens, because alkanes are actually really useful for obviously burning as a fuel and for heating homes and workplaces, but also for getting us around using fuel cars. So and they burn in oxygen completely. So if you've got a plentiful supply of oxygen, then they will produce two products, which is carbon dioxide and water. So alkanes, obviously, they're good as fuels. They produce large amounts of energy, so they've got a good enthalpy change. Obviously, the enthalpy change is quite high, and obviously they're used to power vehicles and factories, and also for Britain. We use natural gas to generate electricity in Britain. Although, like I say, there's a tendency to move away from fossil fuels and use renewables such as solar and wind farms. So that will kind of phase out over the next few years. But as it stands, that's what they're doing. So an equation for complete combustion, you will be expected to be able to write these equations. So this is an example using butane, as you can see here. So you got butane reacting with 6.5 oxygen, producing 4 lots of carbon dioxide and 5 lots of water. You've got to be prepared to be able to balance these equations, okay? You always produce carbon dioxide and water when you have a complete combustion of alkanes. Now, in reality, obviously, you don't always get, in fact, it's rare to get complete combustion. We obviously try and strive to it, but it is feasible to suggest actually that most fuels don't burn completely, and there is some incomplete combustion related to it. And this is when it gets a little bit more serious. So when you've got alkanes burning with a limited supply of oxygen, in other words, there's not enough oxygen there, then we produce a poisonous gas of carbon monoxide, and we produce carbon, which is soot, and obviously this happens when you get incomplete combustion. So let's have a look at a reaction here showing this. So incomplete combustion of butane producing CO and or CO2. So there's your butane reacting with oxygen to form carbon monoxide and water. So obviously carbon monoxide is poisonous, but also it can produce a mixture of carbon monoxide and carbon dioxide, and this just shows you an example of that equation. It's really important, again, when you're writing these out, make sure you balance the equations. Now, in the question, they will tell you if it's incomplete combustion, which products are being produced. Obviously, carbon monoxide is invisible, it's odorless, you can't smell it or taste it, but soot you can. So if they're talking about soot, then it's just carbon. If it's talking about soot and carbon monoxide, then you need to include both on this side. So it just depends what they're asking for, but the principle is it's the fuel with the oxygen, because you need oxygen there, and then whatever products are produced. Whether it's incomplete or complete, you will always produce water though. Okay, so obviously, like we said, carbon monoxide is poisonous. Effectively, it binds to the hemoglobin in your blood. It prevents the red blood cells carrying oxygen around your body, and obviously, that effectively leads to your body shutting down. It's toxic. It's really serious, and so that's why if you have a boiler, normally a gas boiler, you would normally have that in. Normally you'd have that in a garage somewhere, or you would have it away from the house. Sometimes you might have a gas boiler in a bedroom, for example. Ideally, it's not brilliant. So what you would do is you'd have a carbon monoxide alarm near that, so that if there was carbon monoxide leaking from the boiler because it was burning incompletely, then it would wake anybody up who's in that bedroom. So they're really important. We can remove carbon monoxide though by using a catalytic converter. And obviously catalytic converters are fitted into cars, as you may have seen before, so that's obviously going to be quite important. And we'll look at the impacts of this as well, the burning fuels on the environment for this topic. So the incomplete combustion of butane, so this is producing soot, and I've just put the reaction there just to kind of give you an idea of what it looks like. And obviously soot isn't great either. It causes breathing problems. Obviously it's basically, you know what soot is. It's black, and it clogs up, it can clog up engines, it can stick inside of engines, etc. So it's not great. So you can see here, really, if we are burning fuel, we want to try and avoid or try and limit the amount of incomplete combustion that's occurring. Right, so let's look at kind of going back and saying, right, well, how can we remove some of these harmful gases? And you've seen these kind of littered around. These examples come in and out of quite a few of the topics with the CIE syllabus. So you might have seen this already. But you've got when you burn a fuel in a car, you actually produce other gases as well. So one of them is nitrogen monoxide. So nitrogen monoxide is created by reacting nitrogen and oxygen in the air that naturally occurs in the air. It is obviously it gets pushed through your engine. The engine is obviously hot. The spark plugs in the engine as well. If it's petrol, of course, glow plugs if it's a diesel, but it doesn't matter. It's the same thing, and that basically forces nitrogen and oxygen that's in the air anyway to help burn the fuel to bond together and form nitrogen monoxide, as you can see on there, as well as carbon monoxide, as we've seen before. So nitrogen monoxide, as we said before, the nitrogen monoxide is obviously harmful. We'll come on to that in a moment and where that fits in. But cars are fitted with catalytic converters, and they react with the carbon monoxide and nitrogen monoxide before it actually leaves the exhaust. And catalytic converters, they use a rhodium, platinum, and palladium alloys. It's a mixture of different alloys in there. Quite a precious metal, or all of them are. They're very expensive metals, and basically they help to convert carbon monoxide and nitrogen monoxide from burning hydrocarbons in a car to carbon dioxide and nitrogen. And obviously this is fine to release into the atmosphere. This isn't great because obviously it's a greenhouse gas, but it's probably better than carbon monoxide or nitrogen monoxide leaking into the atmosphere. Okay, so let's have a look at some of these then. Obviously, when you burn a hydrocarbon, you do get hydrocarbons which don't burn fully. So ideally in a car or any type of engine, you would burn all the fuel, but in reality that doesn't happen. And some of these unburnt hydrocarbons and your oxides of nitrogen as well that come out of the exhaust do contribute to photochemical smog at lower levels. Now, ozone is a bit of a kind of creates a bit of a problem here. So ozone occurs at the lowest level of the atmosphere, so we call that the troposphere, and this exists as obviously your photochemical smog exists as when you've got sunlight, you've got hydrocarbons and nitrogen dioxide. They mix to form that ozone, and a lot of the hydrocarbons and nitrogen dioxide actually come from cars and factories, obviously from burning them. Now the real problem with that is that when you get solid particles and ozone mixing, so these are unburnt hydrocarbons, then we create this photochemical smog. And this one is an example of photochemical smog in Shanghai. You can see it's very misty, and obviously it's not very good. You don't want to breathe that in because it's not good for your lungs. It damages your lungs, isn't it? So now, the key thing here, though, is that ozone in its own right is also toxic to humans. We shouldn't be breathing in ozone either. And ozone should exist kind of well out of the kind of remits where we breathe. And unfortunately, it can be created through the pollution that we make and obviously put into the atmosphere. So, we need to be aware of these and what the impact of it is. The other kind of environmental side is acid rain. Obviously, when we burn fossil fuels, fuels naturally contain sulfur in these fuels. And then when you burn the fuel, you obviously burn the sulfur. And sulfur reacts with the oxygen that's in the air. That creates sulfur dioxide as well as your oxides of nitrogen. And that then drifts up into the atmosphere, reacts with the water to create acid rain. And you can see in the picture there, acid rain causes a lot of damage to the wildlife, obviously to plants, and to erosion of buildings, and obviously aquatic life as well in the rivers. And obviously, like I said, they do contain these impurities and they produce sulfur dioxide. Now that sulfur dioxide is acidic. Obviously, like we say, it reacts with the water in the atmosphere and it produces sulfuric acid. Nitrates, or oxides of nitrogen, should I say, they do react with water as well and they form nitric acid. So you've got a couple of things going on here. Now, obviously, your nitrates, we've seen how they're created. It's nitrogen and oxygen in the atmosphere. When they come into contact with hot engines because of combustion, then you form your oxides of nitrogen. Okay, and they form nitric acid. So there's a lot of different environmental considerations to take. It's really important that you're aware of the different elements of burning fuels and why we get them and what the impacts are on the environment as well. So ways in which we can reduce the levels of SO2 and NO, or oxides of nitrogen. Normally, it's probably more prominent in manufacturing facilities where they may produce some of these harmful pollutants because they're burning fossil fuels, is we use flue gas scrubbing, basically. So scrubbing is basically where we use wet scrubbing. It's basically where you have your acidic gases going through say a flue, for example, so a chimney, and then what you do is you fire an alkali at the acidic gases, and that's designed to neutralize some like sulfur dioxide and your oxides of nitrogen as well. And effectively, the wet scrubbing, the alkali is calcium carbonate, or we can use calcium oxide, and we dissolve that in water, make a solution that's alkaline, spray that onto the acidic gases, and the idea is that we can then use that, potentially use the byproduct and sell it perhaps, or use it for something else, or dispose of it safely. But we can use, and you'll see later on in the year 1 topic, infrared spectroscopy, and that can be used to monitor pollution levels by identifying bonds in a pollutant molecule, and you'll come onto that a little bit later on, like I say, in a later topic. I think that's topic 22, I believe. So that's the analysis topic, the analysis bit. And obviously we can use infrared to measure how much pollutant is actually present in the atmosphere, and that's how scientists know about the levels of these pollutants in the atmosphere and what can be done. And I know, again, in some areas of the UK, you have congestion charging zones, particularly in the capital and some of the cities as well. And it's really there to try and reduce the levels of these pollutants in hotspots, so areas where there's high traffic. Okay, so we're going to look at, and you would have seen this before, and you'll see this come up quite a few times. Again, you'll probably see it in the halogens topic as well, the haloalkanes topic later on. Or the Halogenoalkanes topic, which I believe is topic 15. But this topic, it comes in here basically because it's an alkane. And alkanes and halogens kind of form the same type of kind of category. So I am going to briefly go through this. But effectively, we can use an alkane and react it with a halogen and to form halogenoalkanes. Now, there's a lot more on halogenoalkanes, like I say, in topic 15. So this is really looking at the alkane bit first. So there's 3 stages to forming a halogenoalkane. And we use this through free radical reactions. And the reaction itself has 3 stages. You've got initiation, propagation, and termination. So initiation, this is where radicals effectively are produced. We use UV light, and we use that to effectively break a bond homolytically, and we produce 2 radicals on the back of it. So we call this a photochemical reaction. Once we've got the radicals will then react with non-radicals, and we call that a propagation stage. So that's basically where the main reaction happens. So you get these chain reactions that keep on reacting and producing new products. And then you obviously have a phase where some of the reactions have to come to an end at some point, and we call that a termination stage. And this is when you have 2 radicals that were produced in the initiation and, say, propagation stage that collide together, and that ends the reaction, so it terminates it. So let's have a look at a specific example, and here we're going to look at obviously making halogenoalkanes. So chloromethane, we can make chloromethane using this reaction here. So you've got methane reacting with chlorine, and that will form chloromethane and hydrochloric acid. So the first step is the initiation step, and this is when you've got sunlight or UV that breaks the Cl bond, so that's in chlorine, and this is a process called photodissociation. So basically we're using light to dissociate, to break a bond. Now, because it's homolytic fission, basically the electron in the bond jumps one way and the other one jumps the other way. So we get an equal split of the electrons. Then we form 2 radicals, which are incredibly reactive. Now, the propagation stage is actually where the chlorine radical here is actually used to make a methyl radical, which is CH3 dot. And then that methyl radical reacts with more chlorine that hasn't been split to make chloromethane, and another Cl dot radical is produced. And then that radical can then react further. So let's have a look at the first example. There's your chlorine radical there, reacting with methane as a molecule. That'll produce your methyl radical with the dot there and hydrochloric acid. So a new radical has been formed. So effectively the hydrogen from here is now part of the chlorine, and then you're left with a CH3 dot. And that CH3 dot, this radical, can then react with chlorine that hasn't been split, and that will form your chloromethane, which is there, and a chlorine radical at the end. And then that radical can then go back to react with more methane to form more methyl radicals, and then that will form more chloromethane. So this reaction will keep on going. As long as you've got a radical and a non-radical, that's the propagation stage. There will come a point when this reaction will stop, and we call this termination. And termination is where you've got 2 radicals that collide together and they make a stable non-radical molecule. So, for example, classic example is here. So you've got your methyl radical reacting with the chlorine radical, and that will form chloromethane, as you can see on there. So you get, if there's loads of Cl dot, so there's loads of chlorine in here, then you will get di, tri, and tetra haloalkanes. So you get loads of them. And if not, you mainly get this single substitution here. So effectively, we've substituted the hydrogen and methane for a chlorine. If you have loads of chlorine knocking around there, let's say you've got large amounts of this compared to methane, then you will get dichloromethane, trichloromethane, tetrachloromethane. You'll probably get multiple substitutions. If not, if you've got a good amount of methane in here and not as much of this, then you're more likely to just get this product here. Okay, so let's have a look at the other side of it, and this is alkenes. So we've looked at alkanes, and they're basically just saturated molecules. They have no double bonds in there at all. Alkenes, on the other hand, are unsaturated hydrocarbons, and they do have a double bond. So the general formula for an alkene with one double bond is CnH2n. Okay, so alkenes, these are hydrocarbons, which means they do contain carbon and hydrogen only, just like an alkane. They're unsaturated. It means they must have at least one double bond. Some alkenes can have more than one double bond. And the types of reactions they undergo are generally addition reactions, because you can add extra molecules to that double bond. And we'll look at some of them reactions later. So let's have a look at the first one. Here, for example, you've got ethene as an example. Or this one, you've got 4 carbons. So this is buta 1,3-diene. So basically, you've got 2 alkenes here, and they're on the first and third carbon here, so it's diene. Double bonds, they have a really high electron density. This makes them, alkenes are pretty reactive, certainly a lot more reactive than alkanes. So with alkanes, to get them to react, you only need UV light. You need to create very reactive radicals. With alkenes, you don't need to go to that level of extreme reaction. Cycloalkenes, so they have two fewer hydrogens than their straight chain versions. So these are straight chain versions here. Obviously, you've basically taken 2 hydrogens away. So this one is called cyclopentene as an example. So very similar to what you had with cycloalkanes. Okay, so let's have a look at some of these reactions then. So as we mentioned, alkenes kind of undergo addition reactions, and they're attacked by electrophiles. Okay, so electrophiles are electron-loving species, or these are species which will target areas where there's a high level of electron density, or they've got a delta negative or negative charge. Now, alkenes have a good level of electrons because they've got a double bond, and obviously this double bond makes it attractive to electrophiles. Now, what electrophiles do is they will add to the molecule. But electrophiles are electron pair acceptors. So remember, nucleophiles are the opposite. So they have to have a lone pair of electrons, and they donate it to an atom when they're reacting. With electrophiles, they accept electrons. So they're deficient in electrons themselves and are naturally attracted to the double bond. So an example, electrophile example, are positive charged ions. So you've got NO2 plus, for example. H plus are examples of electrophiles. You might have polar molecules. HBr can be an electrophile. H2SO4 can be an electrophile. So they don't have to have a proper positive charge. They can have a delta positive charge here. So obviously the hydrogens on here are delta positive. So all electrophilic addition reactions, obviously they have a curly arrow, and you will see more of these curly arrows as well right the way through organic chemistry. So this is basically, curly arrow is it basically call it a mechanism. So a mechanism is basically a diagram to show chemists what happens, or to show people what happens in a reaction. And an arrow represents the movement of electrons. So arrows must go from where electrons are and where they're going to. So in this case, for an alkene, the electrons are actually sitting in the double bond, as you can see there. So there's a high density of electrons. And the arrow moves from the double bonds into the electrophile, which is here. And we're going to use that as a generic example, which is E+. and basically the electrons move into there. So when you're drawing these mechanisms, and we'll see more of these later on, you'll see that's the reason why we're drawing it from there to there. Okay, the general rule is, well, not general rule, you must draw arrows going from a place of where electrons are and where they're going to, and obviously all the electrons are in the double bond here. There's a high density in there anyway. Okay, so let's have a look at some of these reactions of alkenes. And some of these can actually double up as tests for alkenes as well. And you might have seen this one actually, where you can test for alkenes by adding bromine water to it, and it'll decolorize bromine water. So what we're going to do here is look at the reaction, what actually happens when we add bromine water to alkenes. So let's have a look here. So decolorization of bromine water, as I mentioned before. So adding bromine water to an alkene causes a color change, and this is going from browny orange to a colorless solution if an alkene is present. So bromine is obviously browny orange. It's the electrophile, so that's the electrophile, and this adds to the alkene, forming a dibromoalkane. And dibromoalkane is colorless. Get me words out. Right, so let's have a look then. So we've got an alkene here, and this is ethene. So, and then we got your Br2 here. This is your bromine molecule. Now, bromine has an induced dipole on it. So, it's got a delta positive and delta negative. Again, you would have seen this in the bonding topic. I think it's topic 3, when you look at structure and bonding, and we looked at van der Waals forces, so induced dipoles. So, this dipole in bromine doesn't normally have any polarity at all, but it will have a polarity when it comes close to another molecule, which can kind of pull electrons or push electrons away from it, and this dipole exists when it's near something like an alkene. So the Br2 is polarized, okay, so the double bond here is basically pushing the electrons that were sitting here over onto this side of the molecule, so that's basically a van der Waals reaction, but this dipole is created. Now, the electron pair in the double bond here is attracted to the delta positive bromine, and this forms a bond, okay, and it starts to break this double bond across. So let's have a look. There it is. Okay, so electrons going from here on towards this delta positive bromine. Now, this is effectively start to form a bond with bromine, which can only form one bond. So this bond has to break. Okay, so because obviously bromine can't have two bonds. So it breaks that bond and basically sends it on its way. So what we form is this carbocation intermediate. So the bromine that was here is now on the molecule here, but we're now left in a position where this carbon doesn't have enough bonds because it's broken that double bond there. So we have this positive charge that's attached to this carbon. Thankfully, we've got this Br minus that was unceremoniously kind of booted out of this kind of relationship here, and now it's floating around on its own with a lone pair of electrons and a minus charge. You probably might spot this and think, hang on, you've got a positive and a negative charge here, so these are going to attract, aren't they? You'd be absolutely right. So these electrons from this Br minus jump onto that positive charge because obviously there's a strong attraction there between them, and then what you form is colourless 1,2-dibromoethane, and you can see obviously that reaction there. So this is effectively brown, this bit here, browny orange, that's colourless, and when we add that to that, we form this product here, which is colourless, and that's how we can say it's basically a test for alkenes. Quite smart, eh? Right, so let's have a look at some other reactions. So we're going to look at hydration of alkenes, something we all should be doing in this hot weather. Alkenes need water as well. They don't really, but this reaction is obviously, as it suggests, joking aside, is hydration. It means adding water to something. So basically we're just adding water to alkene, and we're going to look at the reaction here. So alcohols are produced when we hydrate an alkene. It's quite useful. So we can use steam, and we use an acid catalyst to get this reaction going, and we can make ethanol by reacting steam and ethene together with phosphoric acid catalyst, and we have a temperature of 300 degrees Celsius and a pressure of 60 atmosphere is needed. Now this would have been quite a common method of producing, say, ethanol or methanol, for example. And actually, this was obviously throughout the pandemic, there was a mass production of alcohol gels, because alcohol is good at killing viruses and bacteria. It's a good sterilizer. So this method would have been one of the methods that would have been kicked into action by large chemical firms to mass produce alcohol gels and cleaning products, and this is one of the reactions they would have had to have done. So alkenes, there we are. So we've got ethene in this case reacting with water, which is steam, and then what we can then do is then obviously react them together with the acid catalyst, and we produce ethanol. It's a reversible reaction with an initial yield of only 5%. That's not pretty. It's not very good, is it? So any unreacted alkene is recycled through, and the overall yield can actually be 90 to 95%. So we can basically just keep reacting it through. So it's quite an efficient reaction. So you can see why it's quite popular. Okay, so let's have a look at another one. Now, don't get this confused with, obviously that was hydration of an alkene. This is hydrogenation of an alkene. Now, hydrogenation is adding hydrogen. Okay, so they come up with all these kind of jazzy names for it. So don't get it confused with hydration. Hydration and hydrogenation are different things. So hydrogenation, we're adding hydrogen to a double bond. Now, we're going to follow the same reaction mechanism of what we've seen before. So we've got this delta positive, delta negative polarity in hydrogen. Now, normally hydrogen doesn't have this polarity. It's induced again. So it's a van der Waals force. So this polarity only exists because this molecule here is coming close to this one, which has loads of electrons in it. And the electrons in this molecule that were evenly spread are now shoved to kind of one side of the molecule, and it creates this dipole. So what happens, just like what we've seen before, is the electrons in this double bond will actually go to the delta positive hydrogen in the H2 molecule. So let's have a look. There it is. Okay, so this will break this double bond. Obviously, hydrogens form a bond here, so this bond will have to break as well. So we basically break that one. And then what we're left with is an intermediate. Now, this intermediate is, just like what we've seen before. There's no difference there. And look what we're left with. We're left with a H minus. This is a hydrogen with 2 electrons in its outer shell, a delta positive carbon, a carbocation, and lo and behold, this is definitely going to attack that because it's just too much of an attractive force for them. And then what we do is we form ethane. So we're forming an alkane from alkene. Now, this might be quite useful if you have surplus alkene, you need to make a fuel again. So it's another reaction of doing that, and this is called hydrogenation of alkenes. Okay, so let's have a look at another reaction. So again, we're going to look at alkenes, but we're going to add halogens to them to form a halogenoalkane. So remember, we looked at the reaction where you took an alkane to form a halogenoalkane. So remember, you had to use UV and incredibly reactive free radicals just to produce a halogenoalkane. With alkenes, you don't need that extreme kind of radical reaction to do that, because alkenes are more reactive than alkanes anyway. They've got this double bond. It's like a ready-made kind of reactive spot, I suppose. So here we're going to look at an example of hydrogen bromide, so HBr. It's going to follow the same mechanism as the addition of a halogen. It doesn't make any difference because they might ask you to do HBr, a hydrogen halide, or it might be just Br2 or Br2, Cl2, etc. So we'd seen obviously the bromine reaction. We've seen that already with alkenes. This is using HBr. So let's have a look. So HBr, the difference with HBr and just normal Br, so Br2, is that HBr is actually a permanent dipole. So there's no induced polarity here. So it's already polarized already. So it's already kind of teed up, ready to go. You've got the double bond, loads of electrons in there. The electrons are going to jump and move towards this delta positive hydrogen. So you can see there's loads of familiarity here. I know it looks as though there's a lot of kind of reactions, but they're all following the same pattern, aren't they? So it shouldn't be too bad. And then the electrons jump from the bond, the HBr bond, onto the bromine, and then we form this carbocation intermediate, again, just like what we've done before. Here we have the Br minus and the carbocation, the C plus. They're obviously going to attack each other because they're obviously very attracted to each other. Attack sounds so brutal, doesn't it? They like each other. And bromoethane is formed. And here we are. There's your bromoethane that's made. So you can see these mechanisms are very, very similar. We're just using different reagents, but the principle and the process is actually the same with all of them. Okay. So this is where it gets a little bit more complicated here, okay? And we need to kind of have our brains switched on. I know it'll all be switched on already. You're probably shouting it is. But you need to have your brain switched on for this bit because it gets a little bit weird at this point. You get different kind of nuances and tweaks here. So, addition of hydrogen halides. I've seen the reaction there. Now, when you react hydrogen halides with an unsymmetrical alkene, it produces two different products. Just when you thought you were getting it, okay? So the amount of the two products is actually determined by the stability of the carbocation intermediate. So remember when we showed them reactions, you had the C+, you had that intermediate in the middle. Now that can be stable or not very stable. Now, the principle which governs the kind of stability of that carbocation is very much based on how many alkyl groups are bonded to that carbocation. And the more alkyl groups you've got bonding to that, the more stable that intermediate is going to be. Okay, so let's have a look. So alkyl groups are, remember, they're just like alkanes. So there might be CH3 groups, there might be CH2, CH3 groups. That's all an alkyl group is. And what these do is these actually push electrons towards the positive carbocation, and it helps to stabilize it. So it's a bit like having I don't know, it's a bit like having the carbocation is very unstable. So it's a bit like a ship that's got holes in it. And if you've got methyl groups, they're like people who are on the ship, helping to try and patch them holes up. The more people you have, the more stable the ship is likely to be because you can stop it from sinking. So let's have a look at this in terms of a chemical version. So here we've got a primary carbocation. So the carbocation is bonded to one methyl group, and you can see it on there. Okay, so the red arrow basically denotes the kind of donation of electrons towards this carbocation, which this is the unstable bit here. The R obviously represents the alkyl group. Now you've got one here. If you had a secondary carbocation, you've obviously got two of these groups pushing electrons into this carbocation, which is going to kind of create a more stable intermediate. And a tertiary one is going to do that even more. So this, if you can form this type of intermediate, that's the best outcome for a reaction to happen. So anything which goes via this intermediate is going to be more likely to happen than by going via this intermediate. Okay. So obviously, because I know we mentioned this before, but in molecules, they're incredibly lazy, okay? Molecules always want to try and follow the lowest energy path possible, and why not? You know, that makes it all right, doesn't it? But so these molecules here, obviously, this is the most stable, so that if you have an option of going via this way, it's just going to go via that way, isn't it? If that doesn't exist or that can't be formed, then it will go for the next stable. So let's actually put some kind of specific examples to this, okay? So here we've got prop-1-ene, okay? So this is definitely an unsymmetrical alkene because the double bond is obviously on the right-hand side of the molecule rather than on the left. So it's definitely unsymmetrical. There's no symmetry there. So here's our HBr here, delta positive, delta negative on the bromine. So we're going to use the same reaction mechanism as what we've seen before, yeah? So we're going to obviously go, electrons move to the delta positive hydrogens, that breaks that bond, and we form this intermediate here, okay? Now look at the carbocation here. This carbon has only got one carbon bonded to it, so it's a primary carbocation. So this is pushing electrons into that carbocation, and that's it. Now if we go the other way, okay, and let's say actually, instead of the hydrogen here, adding onto that carbon there, how about we add this hydrogen onto this carbon on that side, okay? And then what we do is we create the carbocation in the middle, and now all of a sudden we've got two methyl groups pushing electrons into this carbon here. That is a secondary carbocation, and is more stable. So if it's going to choose, if this reaction is going to proceed either via this or this, it's obviously going to choose this route, isn't it? Because it's more stable. So let's work out the reactions. So obviously the electrons from here jump on there and it forms 1 bromopropane, or the second reaction forms 2 bromopropane. Now this is a major product. You're going to get more of this being produced than you are of this one. And this kind of leads into this this rule called Markovnikov's rule. And Markovnikov basically came up with this principle where he said the major product, i.e. this one, because you're going to get more of this being produced, is when we add a hydrogen halide to an unsymmetrical alkene, is where the hydrogen adds to the carbon with the most number of hydrogens already attached to it. So let's go through that. So here's your hydrogen here. Okay, now it is going to, obviously the major product is formed if we add that hydrogen on this carbon, because that's got 2 hydrogens already attached to it, rather than that carbon, which has only got 1 hydrogen. So Markovnikov's rule basically said that the most stable version is where the hydrogen here adds onto a carbon that has the most number of hydrogens, which is going to be this carbon here. And that's exactly what's happened down here. So that hydrogen has added itself onto the carbon with the most number of hydrogens, and so therefore we formed this major product of 2 bromopropane. So that's actually called Markovnikov's rule. So there we are. Try and say that one quick. You get to hear all sorts of exotic names of people, don't you, and different reaction types. So yeah, so basically, as soon as you see an unsymmetrical alkene and you're adding HBr, hydrogen halide, to it, just think of this fella here. All right. Okay, so let's have a look at some other reactions as well. Let's have a look at the oxidation of alkenes. You say you didn't think you could do a lot with alkenes. You can do a lot with it, can't you? It's a bit like, I like to see alkenes a bit like brown sauce. You can kind of add you can use brown sauce with loads of different things like bacon sandwiches, sausage sandwich, I don't know, a burger, anything like that, you know, so you can use that. It's quite versatile. So what we're doing here is basically saying, well, what can you add brown sauce to? So this is basically saying, right, well, you've got alkenes, what can we do with alkenes? And you can do loads of different things with it. So you just need to know them, that's all. Alkenes, they can be oxidized, obviously using acidified manganate ions. So that's the agent that we use, the oxidizing agent. However, the strength of the oxidizing agent, whether it's concentrated or dilute, and the temperature of the reaction matters. Okay, this actually has a big determining factor, and you need to know both of them. Okay, so in this example, we're going to use cold, dilute, acidified manganate ions. Okay, so it's going to be a cold condition, and we're using dilute, acidified manganate ions. Okay, so let's have a look. So you've got your alkene. Okay, we're going to react it with water. Okay, and we're going to obviously have your oxidizing agent. Now, when you do this, when you use an acidified manganate that's cold, we haven't heated up the oxidizing agent, then we get a diol. Okay, so we get 1,2-dihydroxyethane. So we form a diol here. So effectively, we're adding water and a catalyst to form your diol, which is there. So under these conditions, there we are, we produce 2 OH groups and we call them diols. So just be aware of that. Okay, so let's do the same, but this time we're going to use hot concentrated acidified manganate ions instead. So the same reaction, but let's see what we get now. So you've got a hot concentrated oxidizing agent. This is powerful enough to break that C double bond C in alkenes. That's pretty powerful. So we actually form a variety of different products just to kind of complicate things a little bit further. However, it is dependent on what groups represent R1, R2, R3 and R4 in the diagram. Okay, so you can have loads of different things attached to here. So these are just generic groups that we can attach to it. So the R groups could be any alkyl group, that should be B, could be any alkyl group or a hydrogen, for example. So it could be a methane, it could be a hydrogen, for example. And this formula essentially represents all possible alkenes. So these are all the different alkenes that it could be. It's a very generic molecule. Okay. So the products of these reactions can actually helps us to identify an unknown alkene, which is quite useful. So let's have a look at some of these reactions. So the C double bond breaks, and two molecules with a C double bond O group are formed, and we call that a carbonyl group. So you're seeing everything here, aren't you? So a C double bond O, that's called a carbonyl group. So here we are. So we've got an alkene, which is here. So we've got R1, R3, and R2 and R4. We add our oxidizing agent, and it will form this. Okay, so you've got a carbonyl group and another carbonyl group here. Basically what we've done is we've split that bond in half, and we've put an oxygen on both sides of it. Now this is only if it's using hot concentrated, okay, manganate ions. So if R1, R2, R3 and R4 are alkyls, so in other words hydrocarbon groups, then we make a ketone, okay? And if one of them is a hydrogen, then we form an aldehyde. So here you might have R1 and R3. Now if these are two alkyl groups here, we form a ketone. Okay, so that we call a ketone. If one of them is a hydrogen, the other one can be an alkyl, it doesn't matter, then we form an aldehyde. Now you're going to see a lot more of these later on in a future topic beyond this. So you will kind of learn about this a little bit more, but you are expected to know these and what these are in a little bit more detail, so you will see them later on. So if an aldehyde is produced, this can be oxidized further to a carboxylic acid. So if one of these is an aldehyde, so let's say if we had a hydrogen and say a methyl group here, so that would make it an aldehyde, then we can oxidize that further to a carboxylic acid, so we can produce another product as well. So you can see you get a right mixed bag with this type of reaction here. Again, you're going to see a lot more of this in a later topic as well. Let me try and find out which topic it is. It's topic 18. So if you're interested, go to topic 18, and that has a little bit more information. It's also topic 17 as well, so 17 and 18. Okay, so if we have a situation though where both R groups are on the same side of the double bond, for example R1 and R3, then we form a different product. So here's the kind of molecule here. So let's have a look in this red box. So in this situation, an aldehyde is formed, which is methanol, which is there. However, this is easily obviously oxidized further, and we can form carbon dioxide and water. So this is the situation where both R groups are on the same side of the double bond. Okay, so if we're on the same side, so if these are basically identical, then we form this product here. So you can see your two hydrogens there. And then this molecule here can then be used to produce carbon dioxide and water. So in other words, if that and that is a hydrogen and not an alkyl group, then we can produce this product and we can oxidize that, and that will form carbon dioxide and water. So clearly, if we do have an alkene with two hydrogens on this side, and we put it through this reaction here, and we get a gas produced, then we know that on one of the carbons, at least one of the carbons in the alkene, has two hydrogens attached to it on the same side of that double bond. If it didn't, you would never produce carbon dioxide and water. And that's how we can use this type of reaction to help identify what an alkene is. Okay, what type of alkene we have. So you can see it's quite tricky. There's a lot of information here. So the best thing to do is to practice, of course. Okay, so that's it then. So that's the end of this topic for hydrocarbons, which is topic 14. Hopefully that was helpful. Hopefully it was useful. Like I said, the full range of A-level topics for the CIE is on Allery Chemistry YouTube channel. Please hit the subscribe button to show your support. That would be great. Also, these are available to purchase if you wish. I've bundled them together into organic topics, but you can buy the full range for year 1 and year 2. It's great value for money. Use it as part of your revision. The link is in the description box below from the TED shop. Right, that's it then. I hope that was useful. That's it. Bye-bye.